real numbers and their properties. So we're going to get into more numbers. We talked a lot about natural numbers in R1, the counting numbers. We're going to talk about several different kinds of numbers in the real number section here and talk about some of the things that happen with that. We're still going to be dealing with some sets. We're going to be dealing with some pieces of sets and classifying some numbers and what kind is this, and is this a natural number, is it an integer, is it a rational number, and that sort of thing. So the best way that I can describe the number system is with have you ever seen those Russian nesting dolls that like it's one big doll, but you open that up and there's another one inside of it, it's a little smaller. You open that one up and there's another one inside of it, and you just keep going until there's like one in the middle inside that's real small, that sort of thing. So that's kind of how the number system works. The real number system kind of works that way. There's this really big box that's all the numbers in the world that we know of, that we've really learned a lot about. And they're called the complex numbers. Complex, like hard to deal with. And we'll get to the complex numbers at some point in this class. Not tonight, but we will get to the complex numbers. The complex numbers has those imaginary numbers. You may have seen those in high school. It's when you take the square root of a negative number, you get the I that comes into that, and they start throwing more letters in there. But that letter's not a variable. It's a weird letter for I, for imaginary, so it makes it complex. That's what makes it hard. And we'll get into the whole discussion about why they're called imaginary later on. But the complex numbers has numbers that are like that. So you might have, like 2i, negative 3i. Those are some examples of numbers that are complex numbers that are in that box. Well, inside of the big complex number box is a smaller box. I'm trying to pick what color. I'll go dark blue here. It's not smaller by a whole lot, but it's smaller. Inside of that are the real numbers. And the real numbers are numbers that don't have the I on them. Okay? And so that's all the numbers we're kind of more used to dealing with, right? And inside of the real numbers, there's this box that's a little smaller. It's called the rational numbers. So what that does is it creates this other box here. It's called the irrational numbers, because that's the opposite of rational, right? Is irrational. And now let's start talking about what kind of numbers go in those boxes. Okay? If something is a rational number, what does that mean about it? Does anybody know what a rational number really means? Some of them terminate, some of them don't. That's true. That terminating is part of that. You're referring to terminating what?
Like stopping at a decimal.
Stopping decimals, yeah, that's what you mean, okay? When she says terminating, she's saying stopping a decimal, it ends, okay? Decimals are related to what kind of numbers? Decimals are related to what kind of numbers? Where do decimals even come from? Usually division, right? You got $9 and you got to split it between 5 people. There's going to be decimals involved, right? That's division. Look at the first 5 letters of rational. R-A-T-I-O. Ratio. In math class, we have to deal with ratios, right? One of the things you deal with. How do we normally write ratios in math class? Well, there's one way to write them is 1 to 2. But that usually happens at the horse track. That's how they write those. So we don't usually do it that way. We write them as fractions. Rational numbers are numbers that can be written as fractions. Okay? That's an important thing to write down. Maybe over here on the side. Rational numbers can be written as fractions. That's important.
So
1/3 is a fraction, right?
Yeah.
And 1/3 as a decimal is 0.3 repeating.
Yeah, so that would still be rational.
It's still rational because it can be written as a fraction.
Terminates or repeats.
Both could be, yes, absolutely. Now, here's that gets us to the irrational part. That's a decimal that doesn't terminate and it doesn't repeat. Okay, and the irrational numbers, what's included in those are things like square root of 3. Really, the square root of any prime number. And we'll just write prime under the square root. That's usually what's in an irrational number. Those can't be written as fractions because they're decimals that don't repeat and don't terminate. Rational numbers are numbers that can be written as fractions. And so you got like 3/4. You might have like -7/9. That's an example of easily fractions because we've written them as fractions, right? But inside of rational numbers, there's this box that has integers in it. Not integers. Integers are what kind of numbers? Are they fractions? Not usually written as fractions. Could they be written as fractions? Yeah? Give me an example of an integer. How old are you?
28.
That's an integer. 28 is an integer. How could 28 be written as a fraction? 28/1. So that means 28 is an integer and it's a rational number because it could be written as a fraction. Okay, so the way this box works is if you're inside one of the smaller boxes, that smaller box is sitting in the bigger box. So if you're in this small box, you're part of this box, and you're also part of that box, and you're also part of that box. Okay, so if you're an integer, like 28, you're also a rational number, but you're also a real number, but you're also a complex number. Okay, so it's nesting inside of that. Okay, so integers are like positive 28, negative 28, also an integer. Also a rational number because you could write it -28/1, right? Or you could write it -56/2. That's also the same number, right? So integers, positive and negative numbers, like -165, 28, 13, -6. All of those examples of integers. Inside of the integer box, there's another smaller box. It's the whole number box. Or a whole number box. He doesn't have much in him. He's got the number 0. That's all he's got. The whole numbers. He's all, an integer, that's got the negative numbers, right? The whole numbers, normally, whole numbers are 0, 1, 2, 3, 4. But then what do we call the numbers 1, 2, 3, 4, 5, 6, 7 before? Call those natural. So the natural numbers, if you're a natural number, you're a number like 1, 2, 3, 4, 5, 6, 7. Carry on. It count forever. But you're a natural number. But if you're a natural number, what else are you? You're a whole number. If you're a whole number, what else are you? You're an integer. If you're an integer, what else are you? Rational number. If you're a rational number, you're also a real number. If you're a real number, you're also a complex number. So you fit into every category if you're a natural number. Okay? That's the smallest box we get to. There's no subset of the natural numbers that we can talk about that goes from there. Okay, so we've got all these different types of numbers. But if you think about it inside this box type thing, and if you're a visual learner, that box I think can help you. If you're not a visual learner, memorizing those facts can help you. And being able to classify numbers. So that's what we're going to be able to be doing here. Is we're going to classify some numbers, and we're going to do that based on sets. Well, I'm going to give you a set, and I'll ask you to name all the rational numbers in the set. Name all the integers in the set. That sort of thing. out of that. But this nesting idea, that the real numbers are really what we're talking about here. The complex numbers, we haven't got there yet. We'll get there later on in the course, a lot more in Math 110 than in this course, okay? But the rational numbers be written as fractions. The integers, negative numbers, positive numbers, they can be written as fractions as well. Whole numbers, we got the zero thrown in there, but it's still those negative numbers or those positive numbers that are the natural numbers. So we're in this box. That means we're in all the other boxes. Okay, so you got to find out what box do you land in, and then if you land in that box, that means you are in all the boxes that surround you. Okay. All right. Now let's look at an example or two. See if we can kind of apply this a little bit. Example A. We're going to use a set. I'm just going to pick some numbers in this set, and then we're going to list the different types of numbers. We're going to classify the numbers that are in this set. So I've got a -8, -6, a -12 over 4, a -3/4, a 0, a 3/8, a 1/2, a 1, a square root of 2, a square root of 5, and the number 6. Very random set of numbers. Don't know where they came from, just made them up. Okay? We've got this random set of numbers, and what we want to do is take those and classify them. Okay? I want to list the sets of natural numbers, okay? Think about our box, the natural numbers. I'm starting with that set because it's the furthest inside. Okay? If you're a natural number and we fit in this box, then you're going to fit in all the other boxes. Okay? So let's list the natural numbers that are in that set A. 1 and 6. Good. Why is -8 and -6 not in that? They're negative. Negative numbers aren't natural. Negative numbers are integers, right? Okay? So 1 and 6 are the only natural numbers that we have. Now let's go one step outside of that box. The box that's outside of that is whole numbers. And I'm going to put the notation for natural numbers out here to the side. It's a big capital N. But that diagonal bar is doubled up on it. That's the notation for natural numbers if you ever see that. I try to write out natural numbers every time. But sometimes maybe you want to do shorthand for natural numbers. That's what the for natural numbers is. The notation for whole numbers is, well, I did a curvy W. You need to do like that kind of W, and then double up that first mark like that. That's the notation for whole numbers. So let's look at the whole numbers in this set. 0. But if you're a natural number, what else are you? You're also a whole number, right? So 1 and 6 are in that set as well. Okay, so we started on the smallest box. If we're inside of that small box, then we're also inside of the whole numbers box. Right? Okay.
When we were drawing our box photo in the whole number where you put number 0.
But also in the whole number box, there's the other box that's the natural number.
Okay.
So inside of the whole number box is another box. That's where that's coming from. Okay. Good. I'm glad we cleared that up. I think it clicked there. Now, the next box on there was integers, right? I'm going to blow your mind here because the notation is not an I. The notation is a Z. And if you ask me why, I can't tell you. I don't know. It's always been that as far as I know. So the notation for integers is a Z, not an I. Evidently, there's a Greek word that means integer that starts with a Z, evidently. All the Greeks came up with this. So the integers What do we got?
0, 1, 6, -6, -8, 6. I was trying to
Okay, and then what about this -12/4? It's written as a fraction, but what is that? What's -12/4? Is that an integer? Is -3 an integer? Yeah, even though it's written in that form, it's still an integer.
You
just simplified it, right?
Yes, that's exactly what I'm doing. Simplifying the 12/4. Simplifying that to be -3. So that's still considered an integer, even though it doesn't look like one, because it's simplified to be 1. So -12/4. And then y'all said the 0, the 1, and the 6. So far we see 1 and 6 showed up in the smallest box. So that was in the next box, and that was in this box, and you add the 0 to that box, and then we go outside of the integer box and we get to the excuse me, rational numbers box.
Do they have to be in any kind of order? All those negative numbers?
I tend to put them in numerical order. Smallest number first, -8 smaller than -6, -3 smaller than 0, and then 1 and 6. I put them in numerical order. Yeah, that, more logical sense that way.
Okay, what's in my logic? I was saying the natural numbers, the whole number.
Doesn't necessarily have to be in numerical order, but that's how you're going to see them. As answer choices and things on a test, it's going to be in numerical order. Okay, the rational numbers, and this is really going to blow your mind. It's not an R, it's a Q with a little slash through it there. It means rational. And so if we're looking at that set, we want to know the rational numbers. Okay, so that means we're going to have all those plus what? Yeah. And then the square root of 2 and the square root of 5, are they rational? No, they can't be written as fractions. If you did that with the calculator, you get a decimal that doesn't repeat and doesn't terminate. So those are not rational. So let's write our set for those. So we've got -8, -6, -12/4, -3/4, 0, 3/8, 1/2, 1, and 6 are all the rational numbers. Okay. And then we'll go ahead and do the irrational set, since that's the other part of the real numbers. And the notation for irrational is to make the Q and then put a slash through it. That's what it's not rational. That's what that means. And the irrational ones are not subsetted. It's the square root of 2 and the square root of 5. So that's the different ones there with the square root of 2 and the square root of 5. Wish I could do something with this screen here. It's in the way. I don't really know what but that doesn't help, does it? Either way. All right. So we've taken a set and we've classified the numbers inside of it. I'm not going to ask you to do all of them. I may just give you a set and say, find me the rational numbers. Find me the integers. That sort of thing. Yes, sir.
Yeah, like on the rational right there, on the integers and the whole numbers, it's basically just doing like a -8 over 1 to make it a fraction, right?
Mm-hmm. That's exactly right. Yeah. The integers turn into fractions just by putting them over 1. That's exactly right. Perfect. Good. All right. Any other questions about those? Anything going on with that?
On the test, would you just ask us to list one of the sets, or we have to all of them?
I'm going to ask you for one of them. Or I'm not going to ask you for all of them, like all of the different sets from a larger set. I'm going to ask you for one of them. Is all I'm going to ask you for. Okay? I'm not going to ask you for all of them. Okay? All right. Let's see here. Let me make myself organized here. afraid I'm getting a little disorganized. Yeah, we're good. All right, now, so that's the different types of numbers. That's in the same section, believe it or not. It jumps into order of operations and things like that. So order of operations and math have to be together. So my high school students hate it because we go over it every year, and they're no better at it the next year than they were the year before that, and I can't help it. You've got to be able to do it. Okay? So, order of operations, we're going to talk about that a little bit. Okay? Parentheses. And then what? Exponents. Multiplication. Division. Addition. And then subtraction. Order of operations. I learned it with the sentence, please excuse my dear Aunt Sally. That may be what you did. PEMDAS, PEMDAS, maybe how you learned it. I don't know. Maybe you learned it some other limerick or way of knowing that. But parentheses comes first, exponents, then multiplication, division, left to right, and addition, subtraction, left to right. Yes, ma'am. Huh?
It's really from
All right. So, order of operations, parentheses, exponents, multiplication, division, addition, subtraction. We're going to work that left to right in all cases. Keep in mind that multiplication and division are not separate. They are the same level of done. So if there's division that's happening first in a problem before multiplication, moving left to right, then you're going to do the division first because they're technically, mathematically the same operation. Addition and subtraction is the same way. Adding a negative is the same as subtraction. So that's why they're the same. Multiplying by a reciprocal is division, is what that is. That's why they're the same level of work on that. So, all right, so let's first get a little review on exponents. Parentheses, I don't think we need to review on that. We know what those are. We know that the stuff inside of those happens first. So the exponents, a to the n, this a is called the base, and that's the exponent. Together, that whole problem is called a power, technically in math. A lot of times we'll say something like 3 to the power of 5 or something like that, but really 3 to the 5th power is the whole problem out of that. But the base and the exponent. So, example, 4 to the 3rd power. What's 4 to the 3rd power mean? It means 4. Yeah, that's all it means. 4 times 4 times 4 should be 4 times 4 is 16. 4 16s be 64. All right. We can evaluate that. Negative 6 squared. What's that mean? Yeah, negative 6 times negative 6. Positive 36. Remember your rules about multiplying negatives. 2 negatives make a positive. Do that in English too. 2 negatives make a positive. Example D. Now here's the confusing part that everybody always has trouble with. Negative 4 to the 4th. This is where everybody has a problem. Is what's the difference in this problem and this problem other than the numbers are different? This one has parentheses. This one does not. There's a big difference in those. What this says, it says negative whatever 4 to the 4th is. It's not negative 4 raised to the 4th power. It's negative, and then find out what 4 to the 4th is. Okay? So what that means is you got a negative sign, and then 4 to the 4th. That's what that means. That you do negative whatever that answer is.
So it's always going to be a negative answer.
Yes, that's what that tells you. That it's all that the answer, whatever happens here, is going to be negative. That's what that means. Take the negative. And then, so 4 to the 4th power would be 64 times 4, which would be 4 times 60 is 320 no, not 320, 280. Not 280. 4 times 60 is 240 plus 4 times 4 is 256. Is that right? 256. Trying to do it without a calculator. And then you put the negative on it. If you're using the graphing calculator, some of you already have one, be very careful when you're typing that stuff in. So like if you're doing negative 4 to the 4th, like this problem is, you can type it straight in. And we get that negative 256. But if you were doing the negative 6 squared, if you type it in negative 6 squared and hit enter, it's going to square the 6 and then make it negative. But if you mean to square negative 6, you have to put negative 6 in parentheses and square it. And that gets you the proper answer correct. Okay? So with the graphing calculators, you'll have to use parentheses quite a bit there if you're going to evaluate your exponents using that. That's very, very important that you do it the proper way there. Example E. What if we had the negative 4 to the 5th power? Or let's do it an even power, the 6th. Big number. Definitely would probably try to use the calculator to do that one. What should it end up being, a positive or negative number? Why? Because of even power. Yeah, the even power tells me it's going to be positive. If it was an odd power, it'd be negative. Okay, so work it out. 4,096. Big number. 4,096. All right. So quick review of some exponent stuff with numbers and evaluating those. Now let's dive right into the order of operations part of this. So we want to, I guess the instructions would say evaluate or simplify. Just means work it out, get the answer. Example F. 4 times 3 squared plus 6 times 4. And if you got the calculator, you're more than welcome to type it in. That's fine with me. It doesn't bother me. I just want you to understand what should happen first. What should happen first here? No. Parentheses. Please excuse my damn sound. So parentheses comes first. So 4 times 3 is going to happen first. Then we're going to do what? The exponent. So square the 12. And then multiply the 6 times 4. And the last thing you're going to do is add on that. So if we took this step by step, this is what it would look like. 144. And then that turns into 144 plus 24, which would be 168. Is that right? The good thing is with the graphing calculator, you could type that straight in just like it is. So parentheses, 4 times 3, close the parentheses, exponent, raise it to the 2nd power, and then to get out of the exponent, we press the right arrow key, plus 6 times 4. And it follows order of operations to a T. It gets 168. Okay, so if you can type it in correctly, you can get an answer out of it. Pretty good with that. So be careful how you type those in. Okay. All right. Just go here beside that. Example G. 6 divided by 3 plus 2 to the 3rd power times 5. So again, if you type that straight into your calculator, just as it is, it will do it correctly. I promise. It follows order of operations just right. There's no parentheses to deal with here, no negative number to deal with, so it really does work that out kind of nice for you. But what technically should be the first thing that happens? The exponent. So 2 to the third power would be 8. So technically this is what's happening first. And then the next thing would be left to right. Multiplication, division, the same level. So we're going left to right. So 6 divided by 3 technically happens next. But the 8 times 5 happens right after that. So that's 40. 42, right? So sweeping through that with order of operations. Again, the calculator is, fair game on that. I'm not, any way, shape or form saying don't use the calculator. I'm just saying maybe understand what your calculator's doing a little bit so that if it doesn't give you the right answer, you might recognize that doesn't make sense that number ends up being that big or that small. Depending on what you get. All right, let's look at another one. Example H. Let's make it everybody's favorite kind of problem. Big old fraction. But it's still order of operations. Okay. So you got a top part, and you got a bottom part. You just need to follow order of operations on each of those. So the numerator, what happens first in the top? The square root of 3 first, right? So exponents happens before addition. So that'd be 4 plus 9 is what that ends up being, which would be 13 on top, right? What happens first on the bottom? Multiplication. So I'm saying 6 minus 5 times 3. 5 times 3 is 15, right? It's 6 minus 15. What is 6 minus 15? Negative 9, yeah. And then you try to reduce that fraction if at all possible. Does 13 and 9, do they have anything that goes into both of them? No. 13's prime. 9 has 3 that goes into it, but that doesn't go into that either. Don't make it a mixed number. Don't make it a decimal. Leave it as an improper fraction. Reduce it if possible. So like if you ended up with 28 over 16, they're both even, so you could divide them both by 2 and reduce that fraction. But just leave it as an improper fraction. Don't change it to a mixed number or a decimal. That's not how you want to do things. Okay? It's going to help us later on. Let's do one more of those. Negative, parentheses, negative 3, close the parentheses, cubed, plus, and I'll put another set of parentheses in there just because it makes it look hard, but it's not really that bad. Lots of parentheses here, but do any of them mean anything? Not sure. It makes it look tough, right? Yeah, it does. It makes it look tough when they throw all those grouping symbols in there. It kind of makes you nervous, kind of claustrophobic feeling. The walls are closing in on you. You got parentheses in the problem. Brackets. Oh, dear. But it's just a grouping thing, and it really does organize it really well. Because to me, it hyper-focuses me and says, hey, you got to look at this thing, and it's a negative 3 to the third power. Negative 3 times negative 3 times negative 3. Positive or negative? This part is negative, and then this is what turns it to a positive. Yeah. End result is a positive 27 right there because of this negative out in front. Okay? So maybe I'm going to take it step by step there, that there's that negative sign out in front. This turns into negative 27. And then that becomes positive 27. I was thinking right to 5. Positive 27 plus negative 5. Okay. And then we'll get that last step in just a second. Let's go ahead and get the denominator going. What happens first here? Multiplication. So we're going to multiply 2 times negative 8, and then we're going to multiply 5 times 3, right? Those are the things we're going to do first. So that'd be negative 16 minus 15, right? And then I'm going to get that answer. Negative 16 minus 15. That makes it more negative, right? That'd be negative 31. And then on the top, 27 plus negative 5 is the same thing as 27 minus 5, 22, over negative 31. And then you try to reduce that if possible. Just anything going to 22 that goes into 31. 31's a prime number. 22 is not, but 31 is, so nothing we can do. Got it in simplest form there. Leave it as a fraction. Okay. All right. Let's do a little bit more evaluating. Let's go one more step further with it. And let's evaluate when x equals negative 2, y equals 5, and z equals negative 3. And I usually make my z's with a little slash through them. They look kind of funny, but they also look like a lot like 2's sometimes, so that's why I put a slash through them. So if you see a slash through it, you know it's a z. It's not a 2. Okay? So evaluate when those letters equal what they equal. Let's do negative 4x squared minus 7y plus 4z. Okay? So if we're going to evaluate for those particular values for the variables, what's that mean I'm going to do? Very good. Put the numbers in the place of the variables and put them in parentheses. That'll help you out, especially on the exponent parts. Okay? I, by default, always put them in parentheses. That way, if there's a negative sign, it doesn't mess me up. Once I've done that, I can go straight into the calculator with that. If I use the parentheses every time on purpose, then my calculator will not mess it up if I type it in just like that. So you could type that in the calculator, work it out if you wanted to. You can do it without it. It'd be 4 times negative 4 is negative 16 minus 35 minus 12, or plus negative 12 if you want to put it that way. And then work this out, which would be negative 40, or no, negative 51 minus 12 would be negative 63. Again, I'm not anti-calculator. I'm just trying to do it step by step so that if we come up with something wrong on the calculator, that this is really what's happening. This is what the calculator is doing in the background. By all means, you're welcome to type that in and get an answer. That's not. I'm not saying don't use a calculator. I'm just trying to not use it on purpose. All right, let's do one more. Let's say x is equal to negative 2. Well, we're still there. We can still see that. So I'm just going to write that example there. 2 parentheses x minus 5. Then the squared on the outside of those parentheses. Plus 4y. And then a big division symbol. Z plus 4 on the bottom. And we're using these x, y, and z values. That's the ones we're using. We'll scroll up a little bit more so you can see from the back. So what are we going to do first? Yeah, replace those variables. Change all the variables to the right number. So everywhere there's an x, I'm going to put a negative 2 in parentheses. So 2, negative 2, plus 4 times 5, over negative 3 plus 4. Technically put that in parentheses, no, even though it doesn't really need it there. And then work that sucker out. So parentheses comes first in order of operations. So we got to do this part first. Negative 2 minus 5 would be negative 7. So we really have 2 times negative 7 squared. And I'm going to go ahead and do that 20 there because it's kind of separated. And I'm going to go ahead and get that as B1 because I can go ahead and do that work down there. I'm simplifying the numerator separate than I am the denominator and then working it as one thing. So that ends up being 2 times 49 excuse me, plus 20. And what's 2 times 49? 2 times 50 would be 100. 2 less than that would be 98 plus 20. Should be 118. And it's over 1, so that just makes it that number. Lose the denominator there. And again, if you're going to do this with the calculator, you're going to need more parentheses, really. If you wanted to do the whole thing at once, you would need to put the top part in a set of parentheses, the division symbol, and then put this in a set of parentheses if you wanted to do it all at once. I would probably do the top part, calculator, then do the bottom part as a separate problem, and then do the division with the calculator after that. That saves me from having so many parentheses in the problem. Okay, so be careful of that. All right. One more quick thing in this section. It's power pack section. A lot of stuff going on in it. Let's talk about simplifying. If we're going to simplify an expression, expressions usually have variables in them. That's the difference in what we're doing here. We were simplifying numerical expressions a while ago. We were evaluating them for numbers for the variable. What we're going to be doing in this little part of this section is we're going to be taking pieces and simplifying the expression by putting the like terms together. So maybe you've heard that word before. Like terms. Okay. If you can hang with me for 3 more examples, we'll get a break. Okay? 3 more examples. Maybe 4 more examples. Sorry, lied to you. Example L. Really easy one to start off with. All right, so we have a 6 plus parentheses 9 plus x. Okay, so we've got this expression. They want us to simplify it. So we got to put the like terms together. Well, what's the like terms in this problem? The 6 and the 9. How do you put them together? A plus sign, right? The parentheses really don't matter. They just grouped this stuff together. But 6 and 9 are like terms. So we're going to go ahead and add 6 plus 9, which is 15 plus x. And we got our answer. Simplified an expression. Like terms. Kim? Let's say we have this expression. 7 minus 2 plus 3x, close the parentheses, plus 6 squared plus 5x. So a lot going on in this one, but we're simplifying, so we're getting all the like stuff together. Keep in mind, though, we still have to follow what? Order of operations is still in the game. Okay? So even though we're not just doing an order of operations problem, those rules still apply. So what happens first? Well, you can put your variables together. You could because they're like terms and there's nothing happening. But technically, the order of operations tells us to do the parentheses first, and you would subtract 7 minus 2 and get 5 plus 3x. And then the next thing in order of operations would be 6 squared would be 36, right? And then, yes, I mean, it's not going to be wrong to go ahead and get the x's together, but just be careful of that. So 3x plus 5x, 8x, 5 plus 36, 41. Sure. 8x plus 41. Or if you wrote 41 plus 8x, that's the same thing. Yeah, and it does. I'm not picky about it right now. When we get later on, there will be a rhyme and reason to putting it in that order like that, but I'm not going to be picky about it right now. All right. Example N. Let's throw a fraction in there. 5 over 8 times 16y plus 3 times 2y. So throw a little fraction in there just because we need it. Life's a fraction. Once your life is no longer a fraction, it's over. Because you've lived the full thing. So What operation's going on between the 5/8 and the 16? When it's written like that. They're multiplying. So when they're mashed together like that, they're multiplying. So we're multiplying 5/8 times 16y. Do they have to be the same to multiply them? You can multiply any two things together. You just can't add or subtract unlike things. So 5/8 times 16, how much is that? Maybe it helps to put the 16 over 1. And then you can multiply straight across if you want to. You could say 5 times 16, and then 8 times 1, and then reduce it. Or, somebody remember doing something called cross-canceling? Maybe way back when? It's been a while, probably. Yeah, it ends up being 80 over 8, which ends up being 10, right? 8 goes into itself once and into 16 2 times. What's 5 times 2? It's that same 10 that we got there. And then over here, 3 times 2y would be 6y. And we end up back with 16y as a final answer there with that. So multiplying first, because order of operations said multiply first. Yes, sir?
You saw in the last example that you could like combine the like terms first?
You could have.
Now, how would you do
You
it?
couldn't do it with this one.
Okay.
Because they're both multiplied by something first. On the previous example, this 3x wasn't multiplied by anything, and neither was the 5x. So they weren't affected by anything. This is the reason you could have technically put them together first.
So if they're separated from the other and they're going
Then you could. Yeah, you could. You don't have to. I would recommend following order of operations, the whole way through. That way you don't erroneously do them in the wrong order when they really should have been done something with first. Okay? Let's look at one more, and then we'll take a break. Let's say we had 10x parentheses 6 over 5 minus 3x plus 13y. A little bit more going on. Got an extra, got another term over there. What should happen first?
10 over 1.
Well, what's going on between this 10x and the 6 over 5? Multiplication, yeah. So, yeah, you could make that 10 over 1, yeah. If it helps you.
I was thinking at first it was, but didn't know because the X threw me off.
That x being there, really, it's just hanging out, waiting for you to do something with its numbers. And then, so 10 over 1 times 6 over 5, 60 over 5, which is 12x. Is that right? Okay. And then what are the like terms from there? Yeah, 12 minus 3 would be... Is it okay that I didn't end up with just one term? Yeah. Those are not like terms. I can't put them together. One's an X and one's a Y. They don't match up, so they don't go together. Okay. All right. Let's take us a little break.